Here's my latest robot. I call it Macro Mouse because it's a larger Lego version of a Micro Mouse, which is a college-level robot designed for a college-level robotics competition. This robot's able to do many of the same things as a Micro Mouse, which is navigate through a maze, and it does that using two. It's pretty standard. It has two drive motors to make it go forward and backward, and turn left and right. It also has a third motor, which it uses to turn a sensor so that it can detect walls around it. This is an EOPD sensor. I had to use an EOPD sensor instead of the ultrasonic sensor just mainly because it was more consistent, more precise, and just functioned much better inside the maze.
Here you can see the Macro Mouse at work in a macro maze. In the upper right hand corner you'll see a map start to appear that shows what the mouse, the information the mouse has stored or is considering and using when it's making its decisions. You'll see it's already detected two walls and that it's created a series of values that indicate which path it should take to get to the target cell. It always shoots for the value that's lowest with respect to any neighboring cells. I like this activity because I believe it's the first activity I've seen that's accessible to high school age students that requires a much higher level of thinking and problem solving than say the FLL, the FTC competition, because it requires students to build a robot that stores information in a very sophisticated manner and then sifts through that information to make intelligent decisions. In short, it requires students to build a robot that thinks. You'll see now that the mouse has made it to the end. It's realized it solved the maze. I'm going to go ahead and restart the mouse from the beginning using the same program but slightly altering the maze. This will prevent the mouse from solving it the way it did in the past, yet it will still solve it as it did before. You'll also notice that this maze it's actually not a maze, it's what's called a labyrinth. There's no beginning and end, and it's impossible to solve it simply by following a wall, which a lot of robots tend to do at the basic level. This robot actually has to create some sort of map and track its movement in order to know where it's at on the table and how to get to the end, and that it's arrived at the end. This robot, you'll also notice, makes it has several different ways of correcting its position. You'll notice that it makes slight changes to its heading each time it enters a cell. It also bumps into walls when it knows that the wall exists, both in the front and the back. That's to, so to say, square it up to the world. The one problem that this mouse has is if it finds itself in a dead end and it needs to make a 180, it doesn't do that so well. It's a design flaw that I need to work on, and I hope somebody looks at this and makes some vast improvements, because I'm very ready and willing to admit that this is nothing more than a proof of concept video and program and design, so that hopefully other teachers out there can encourage their students to engage in such an activity and solve it in a much more efficient manner. Here you can see the flood fill algorithm at work in slow motion. The way it works is it begins with the target cell at a value of 0 and then makes the neighboring cells a value 1 higher than that. And it iterates through the entire maze until every single cell has been assigned a value relative to that target cell. Here you can see the flood fill algorithm at work again in slow motion, but this time with a maze hard-coded in so that I could test to see whether my algorithms would work correctly. Notice that neighboring cell values are only updated in the event that no wall separates those two cells. And obviously the route's a little bit longer.